In this episode, we will learn about evaluation of AI systems. Evaluation is especially critical for AI systems because their behavior is non deterministic. There is rarely a single fixed correct answer for a given question. Unlike traditional software that follows predefined logic and produces predictable outputs, AI systems generate responses whose quality can vary widely. The same input prompt can generate multiple plausible answers. Some of these could be accurate and helpful, others can be incomplete, misleading, or outright hallucinated. And this challenge is further amplified with agentic AI systems that create dynamic execution plans and execute a variety of different actions on behalf of the user. Therefore, with AI systems, we cannot rely on a simple pass or fail test. Rather, we measure the quality of the response across various dimensions such as accuracy, safety, relevance, and usefulness. And this is done both at design time and continuously in production so that we can catch silent quality failures. And this shift from exact matching to quality assessment is what makes AI evaluation fundamentally different than the kind of evaluation we are so used to with traditional systems. Let us understand what should be evaluated in an AI application. An AI application is composed of multiple components, starting with prompt, followed by retrieval, the agent, workflow orchestration, and finally the response that is delivered to the end user. Each of these stages can introduce different types of failure, which means evaluation cannot happen only at the end, it needs to be continuous throughout different stages of the entire application. And amongst the dimensions of evaluation is quality, where we measure that response is accurate, relevant, and genuinely useful to the end user. Next is safety, which measures if the system is avoiding harmful outputs, protecting sensitive data, and complying with organizational policies. Performance is also critical as with any other application. Users expect fast responses even when underlying systems become complex. In production environments, operational metrics also become equally important. Reliability measures whether the system behaves consistently over time. Cost ensures the application remains economically viable at scale. An ultimate goal of evaluation is to deliver real value to the end user. Even the most technically sophisticated AI system is useless if it cannot consistently help the end user accomplish their tasks. And observability gives visibility into what is happening inside the system so that we can debug issues, improve performance, and continuously optimize the application. Let us look at some evaluation metrics for retrieval augmented generation. A retrieval augmented generation system has two core responsibilities. First, it must retrieve the right information, and second, the language model must use this information correctly when generating a response. To evaluate this, we typically use three key metrics. The first is retrieval relevance, which is also known as precision. In this, we evaluate of all documents that have been retrieved, how many are actually relevant to the user's question. Retrieving too many unrelated documents can reduce the precision and make it harder for the model to focus on the right information. The second metric for RAG systems is context completeness or recall. In this, we measure whether we have retrieved all the information that is needed to fully answer the question. Even if every retrieved document is relevant, we can still miss critical piece of information, which can lead to incomplete answer. The third metric for RAG systems is answer groundedness, which is also called faithfulness. This metric is different from the other two metrics because it evaluates the language model rather than retrieval system. Even when the retrieval is complete and correct, the model can still introduce unsupported claims or hallucinations. Groundedness checks whether every part of the generated answer is actually supported by the retrieved context. Together, these three metrics help us answer three important questions. Did we retrieve the right information? Did we retrieve enough information? And did the model use this information faithfully when generating the response? To understand these metrics more deeply, let us see how recall is calculated. In order to calculate recall, we start with ground truth, which is a complete set of correct information that we want the system to retrieve for a given question. Ground truth data is built by domain experts or subject matter experts who decide which piece of information is truly relevant and correct for a given question. In this example, there are 6 relevant steps which are required to reset the password. The retrieval system has only returned 5 steps, out of which 4 match the ground truth, whereas one, which is enable MFA, is not relevant. One of the required steps, as in the ground truth, was missed entirely. The recall measures coverage, so it asks of all the relevant documents that are in the ground truth, how much did we actually retrieve? The formula is relevant items that have been retrieved divided by the total relevant items, which in this case is 4 over 6. A low value for recall means the language model may never see important information because it was never retrieved. Even the best LLM cannot generate an answer from incomplete information. Now let us look at the other side of retrieval quality, which is precision. Precision evaluates whether what we retrieved is actually relevant. In this example, the retriever returned 5 items, out of which only 4 are relevant. The formula for precision is relevant items retrieved divided by total items retrieved, which in this case is 4 over 5. A high value of precision means that system has retrieved mostly correct information, whereas a low precision means that system is passing extra unnecessary context to the model, which can increase token usage and therefore cost, and it can also lead to incorrect and hallucinated response. So, recall asks whether we retrieved enough information, whereas precision asks whether we retrieved only what was needed. A good retrieval augmented generation system needs a high value for both these metrics. While recall and precision are objective metrics that require golden dataset, the groundedness is a semantic evaluation which is performed using a large language model as a judge. The evaluator looks at 3 inputs, which is the original question, the retrieved context, and the generated response. In this example, the context says employees receive 20 vacation days after 1 year. But the answer adds 5 personal days, which does not appear in the evidence. To evaluate this, we use another large language model as a judge, and the judge follows a developer defined rubric. The rubric is written directly into the evaluation prompt and it asks 3 things. Are the claims supported by retrieved context? Does the answer introduce unsupported information? And does it avoid contradictions? In this case, the answer fails the unsupported information check because 5 personal days was invented by the model. The evaluator gives its groundedness score and also gives a reasoning of why it is giving that score. And this is the value of LLM as a judge, as it does a semantic evaluation, providing both the score and the reasoning behind that score. The reasoning is based on clear rubric rather than exact string matching. Now let us look at some more metrics that evaluate the response quality. The first metric for evaluating the quality of a response is factual correctness. In this example, response says that employees receive 30 vacation days, but if the company policy says that these days should be 20, the answer is incorrect and should be blocked. This kind of an error might come from model's hallucination or from sending wrong context to the model. In either case, detecting factual errors in the generated response provides an important guardrail for the system before it reaches the end user. Another evaluation metric for response is completeness. Here, the user prompt asks for benefits, challenges, and best practices, but the generated response only covers first two and misses best practices. Therefore, the evaluation result is that response is incomplete. The third key evaluation metric for response quality is relevance of the generated response with user's query. The evaluator LLM does a semantic check between the response and user's question based on the rubric that is provided to it. In this example, the user asks how to reset AWS password, but the response talks about IAM users and roles. It is related to AWS, but it doesn't address user's intent. So the evaluation result is that the response is not relevant to user's query. It is important to note that each of these is a semantic evaluation, so they are done using a large language model as a judge, and they are independent of each other. A response can be correct but incomplete, grounded but not relevant, or relevant but factually wrong. This is why production evaluation almost always measures multiple dimensions instead of relying on a single score. Now that we have seen some examples of evaluation metrics and we have seen how some of them are objective in nature, the others are semantic evaluation metrics, let us see how we can design effective evaluation metrics for a particular use case. The first category of metrics is objective metrics, and these are deterministic measurements that do not require an LLM or a human judgment. Examples of these metrics are schema validation, latency checks, cost checks that can be monitored continuously in the production. Precision and recall are usually measured at design time or offline because they require benchmark data, also known as ground truth. We may not have that for production traffic. The second category is the semantic evaluation using an LLM as a judge. These metrics help evaluate semantic qualities such as groundedness, correctness, completeness, and relevance, as we just saw. Many of these can also be automated in production using LLM and a well defined rubric. Some qualities are more subjective, such as helpfulness, brand voice, or user preferences, and these qualities require human evaluation. Humans can be involved, especially during development, experimentation, and they can also do a periodic review of production traffic. Like any other system, we must have business impact metrics. AI success is not just about model quality, it is also about the value that system delivers to the business use case, which is why teams also track task success, end user satisfaction, end user engagement, and cost efficiency. The important point here is that no single metric is sufficient. A strong AI evaluation system combines offline benchmarks, production monitoring, LLM based evaluation, human feedbacks, and business KPIs to create a complete view of quality of the system. So far, we have discussed why we need evaluation for AI systems and what should we evaluate for AI systems. The next question is, how do we actually perform these evaluations? Let us start by looking at the foundation of any offline evaluation, which is a golden dataset. When we discussed recall and precision, we talked about golden datasets, which are curated collection of high quality test cases that are used to measure the quality of the AI system. Each test case includes expected reference outcome against which the system can be evaluated. This is similar to the unit tests that we create in traditional software, and like a good unit test, a good golden dataset is built from multiple sources. These include real user queries, production logs, subject matter expert review, failed production cases, and synthetic edge cases for better coverage. These examples are then reviewed, deduplicated, validated, and labeled with expected response or expected behavior. The exact structure of golden dataset depends upon what we are evaluating. For end-to-end AI system evaluation, it typically contains the user queries and their expected responses. For intermediate evaluation of retrieval system, it may contain user query along with relevant ground truth documents or chunks as we saw in the example earlier. For evaluating guardrails or agents, the golden data set may include the expected classifications, policy decisions, tool calls, or workflow steps. Regardless of the format, the goal of golden data set is to provide reliable benchmark data that can allow us to evaluate the AI system consistently. For evaluating the system, before we use a large language model to judge the response quality, the first run is typically objective validation, which is simple deterministic checks that are fast and cheap. We verify things such as output schema, required fields, citations, safety rules, PII, and basic constraints such as the length of the output or regular expression patterns, etc. If a response is missing a required citation, it can fail immediately as a result of objective validation, even if it looks reasonable as a response. If the objective check fails, we fail fast and do not waste time in calling a large language model for semantic evaluation. However, if the response passes the objective validation, we move on to the semantic evaluation, where, as we've seen in the previous examples, we use another large language model as an evaluator. The evaluator takes into consideration the inputs of the user question, the retrieved context, and AI generated answer, and also uses a clear rubric created by the developer or SMEs that specifies what to measure. It is important to understand that evaluator LLM is not generating a better answer, it is simply scoring the existing answer against criteria such as groundedness, completeness, etc. Finally, the large language model returns structured scores, often with a short reasoning for each metric. These semantic scores approximate how a human would have judged the response quality, but they remain fully automated and scalable. This is an example of how an evaluation rubric could look like. Rubrics are defined by developers, domain experts, or SMEs, and they clearly explain each metric, what the evaluator should look for, and what counts as excellent, average, or a poor response. For example, for correctness, a score of 5 could mean that all factual claims are accurate, while a score of 1 could indicate major factual errors or hallucinations. For groundedness, rubric may require that every claim be supported by provided context. The rubric also defines the expected output format from evaluator LLM, such as a structured JSON that makes it easier to automate, analyze, and integrate the response into a larger evaluation pipeline. Now that we know the evaluation metrics and how the evaluation criteria is defined, let us look at where these evaluations actually fit into the overall development and production lifecycle. Whenever we make a change to an AI application, whether it is a new prompt, an updated RAG pipeline, a different model, or a modified agent workflow, we do not send it directly to production. Just like with traditional applications, even with AI applications, we first evaluate the candidate release set against a golden data set. And this process is called offline evaluation. The process starts by running the candidate release against examples in the golden data set and recording the traces and logs. These traces and logs are then used to run objective rule based checks such as schema validation, policy compliance, safety rules, etc. After running these fast and inexpensive checks, if the release passes, we move to semantic checks using a large language model. At this stage, the evaluator model measures semantic qualities using developer defined rubrics, as we discussed earlier. If the evaluator model has high confidence in the response, we can rely on the automated scores. However, if the model has low confidence or the result is ambiguous, we can route the case to a human reviewer for a more subjective evaluation. Finally, all the results are consolidated into an evaluation report that contains scores, evidence, feedback, and deployment recommendation. If the release meets all the required quality thresholds, it moves forward. Otherwise, it goes back into the development cycle, issues are fixed, and the evaluation pipeline is repeated. In order to take deployment decision, organizations typically have a release criteria which consists of multiple quality gates that every release must satisfy. The first gate is the objective validation check. Next, semantic evaluation checks using large language model. For AI agents, we also evaluate task status, whether agent can consistently complete the intended business task. Organizations also verify safety by checking for critical policy violations and also ensuring that low severity issues remain within acceptable limits. And typically, the final quality check is that of performance and reliability through operational metrics such as latency and error rates. Only when the candidate release passes every quality gate, we allow it to be released through staging or canary deployment into production. For AI applications, a pre release evaluation is not enough. We must also continuously evaluate application once it's deployed in production to monitor its quality and to make sure that it is not degrading over time. When a user sends a request, the system responds back immediately and, as a background process, saves logs such as production telemetry, which includes response logs, tool calls, any agent traces, safety events, latency, errors, etc. System also logs user signals such as explicit user feedback, task status, and customer escalations. We then take a sampled portion of this live traffic for evaluation using the same techniques as we saw with offline evaluation, which is objective rule based checks and semantic checks using LLM as a judge. However, we do not have any golden data set in online evaluation because this is live traffic. So, objective checks have to be such that they do not rely on any golden data set. The results of these evaluations are used to create reports and visuals on dashboards that show trends, highlight any regressions, and trigger alerts when quality begins to degrade. Teams can use these insights to refine prompts, retrieval, agent logic, workflow, etc., creating a continuous improvement loop. Throughout this presentation, we focused on evaluation. However, evaluation of any system cannot happen unless we have traces, logs, metrics, and user signals to use for evaluation. We need visibility across the entire path of AI application, which includes application logic, model inference, tools or retrieval, the final response, and also the user's feedback. That is why OpenTelemetry sits at the center of this diagram that shows the tools for AI evaluation. Once we have the telemetry, we can use tools such as Phoenix, Langsmith, and Langfuse for debugging, Arise for AI quality monitoring, Datadog for infrastructure and operational monitoring. So, the key point is that just like with any other system, observability of an AI system is the foundation for monitoring the quality, diagnosing issues, and continuously improving the system. This brings us to the end of this session on AI evaluation, where we learned about why AI systems require a different quality based approach of evaluation. Then we learned about the quality metrics themselves across retrieval and response. We also learned about creating golden data set and evaluation rubrics, and then use them in offline evaluations in CI/CD pipelines and also in online evaluation of production systems.